Hi, this is Guillermo Campitelli, and in this video I'm going to explain continuous distributions using the drone delivery metaphor. Okay, so first of all, the continuous uniform distribution. Basically, even though the formula may look complicated, is rather easy. So basically, on the continuous uniform distribution, the values could be, it's not a characteristic of the distribution, could be negative, could be positive, and so there is no restriction. Now, the shape of the distribution is the main characteristic of this distribution. Basically, in a uniform distribution, all the values within the interval have the same probability density. And values outside the interval that we are interested in have zero probability density. Okay, so basically this is the continuous distribution. Now, how does it look like in terms of a typical graphs that we use? This is the look of the continuous uniform distribution. So basically, same density for all the values within an interval, and values outside the interval, the probability density is zero. So basically, this continuous uniform distribution, or any continuous uniform distribution, has two parameters, which is the parameter A and B, or parameter minimum, parameter maximum. So basically, A is the lower bound of the interval and B is the upper bound of the interval. So in this case, A is minus 0.4 and B equals 0.4. So basically, that's the interval. Now, what's the density? The density is 1 divided by B minus A. So B minus A is 0.4 minus 0.4. That is 0.8. So that's the length of the interval. So the density is 1 divided by the length of the interval, which is 1 divided by 0.8. That is 1.25. So the probability is density for all the values within the interval is 1.25. And the values outside this interval is 0. And we can show that this integrates to 1, doesn't add to 1, because we've got densities greater than 1, by determining the probability mass of the interval. So the probability mass of the interval is the density times the length of the interval. So the density is 1.25 and the length is 0.8. 125 times 0.8 equals 1. So it integrates to 1. This is a way of showing that it integrates to 1 without using calculus. And obviously it's very easy in the continuous uniform distribution, but it's not so easy in other distributions. Okay, so this is the main aspect of the continuous uniform distribution, is that it's uniform, the shape of the distribution. There is a discrete uniform distribution, which I didn't show in the previous videos, because it's equivalent to a categorical distribution with equal probabilities in each category. Okay, so the idea is the same. The probability of each value is the same. Okay, the most important, the most popular distribution among psychological researchers is the normal distribution. Not only psychological researchers, researchers in every area, they use the normal distribution a lot. So I'm going to show you the formula, but in terms of the metaphor, the drone delivery metaphor, basically the idea is that we've got a city in which there are no regions, but we've got a kilometer zero of the city, which with an imaginary line across the city with the kilometer zero, and then we can measure the distance between each point in the city to kilometer zero. So to the right or to the east will be positive numbers, to the west will be negative numbers. So in this city, 34% of the population is located between kilometer 0 and kilometer 1. 34% of the population is located between kilometer 0 and kilometer -1. Then 13.6 people live between kilometer -1 and -2, and 13.6 between kilometers 1 and kilometer 2. So you can see that there is a symmetry. So this is the shape of the distribution, and that a normal distribution is the main characteristic is the shape. The shape is symmetric. Of course, here we are talking about intervals 0 to 1, and we can determine the probability mass of intervals, but as explained in a previous video, we cannot determine the probability mass for a continuous value, but we can establish the probability density of very tiny intervals. So the formula for probability density in the normal distribution is this one. Now it is complicated, and I'm just going to explain a few aspects of it. This pi number has nothing to do with the pi we use in probabilities in previous distributions. It's the actual pi number. So the pi number is 3.14, etc. This E is the Euler number, which is 2.71 something. Doesn't really matter. What matters are the x. So x is the value we are interested in determine what the density is. So it could be 0, it could be -1, 1, 2, 3, 7, etc. Now the mu, what we call the centrality parameter, and the sigma is the dispersion parameter, and typically we call it the standard deviation, and sigma square is typically called the variance. So it's the square of the standard deviation is the variance. Now it doesn't matter what the formula does. What it matters is that when values are lower than the centrality parameter, then the probability is given in this from 0 to negative numbers. When the value is higher, then the probabilities, so we are talking about these values, and the probabilities associated with them will be here. The sigma will determine how flat is this curve. So if the sigma is very large, then this curve will be flatter, flat. If the sigma is very small, then there will be a very huge peak here, and so the values will be very highly likely, very close to the centrality parameter, and to the mean, which is 0, and as soon as they go away from 0, the values are very, very unlikely. But if the sigma is large, then this is not going to be very peaky. It will be lower, and so there will be values that are further away. They will be relatively more likely than in the current distribution. So these are the things that we need to take into account for the normal distribution. Now, here the mean of this distribution is 0. It is not necessarily the case. We can have normal distributions with any type of mean. We just have to add the mean to all these values in order to obtain such distribution. So basically, when you apply this formula, it will be centered to 0. But you can, if you add the mean of your data to all these values, then you will have the same distribution but centered around the mean of your data. So the procedure to obtain the distribution is this one. The values are from negative infinity to positive infinity, and they are continuous. And what is most characteristic of the distribution is the shape, the symmetrical shape of the distribution. Okay, so finally, the beta distribution. The beta distribution, as you can see here, it is important that the values are between 0 and 1. And this is a distribution that is not very well known among psychological researchers. But those who do Bayesian statistics, they really like the beta distribution. Why? Because it's a distribution that allows to assign probabilities to probabilities. So Bayesian researchers assign probabilities to anything, whereas frequentist researchers, they can't assign probabilities to anything. They assign probabilities to a small number of things. And the Bayesian researchers need to assign probabilities to probabilities. And so that's why the beta distribution is fantastic, because you can assign probabilities to values between 0 and 1, and probabilities are values between 0 and 1. Okay, again, this in terms of the metaphor, it would be a city in which we've got boundaries in the city. It's not like in the uniform distribution and in the normal distribution that there are no clear boundaries. Here the city has clear boundaries, and the left boundary of the west boundary is, we arbitrarily call it 0, and the right or the east boundary we call it 1, and then this is a continuous distribution, not discrete, so we cannot assign a probability mass to each value, but we can assign a probability mass to an interval. So here is one beta distribution in which we assign probability mass to intervals. This is the probability mass for interval between 0 and 0.1. This one, the probability mass for values between 0.1 and 0.2, and so on and so forth. So these values will add to 1, but this is not what we typically do. What we typically do is to assign probability densities to values. And I'm not going to show you the formula, because that formula is really, really complicated. An important thing is that the beta distribution has two parameters, shape 1 and shape 2, or sometimes called alpha and beta. So basically, and the way they work, you have to see it, how it works. So I'm going to go to this website in which there is an applet to use the to play around with the parameters, the two parameters of the beta distribution, and see the shape. So important thing of the beta distribution is the values between. You can use it for values between 0 and 1, which is very useful for Bayesian statistics. The shape varies depending on the values of the parameters shape 1 and shape 2, or alpha and beta. And the procedure is a very complex formula that I'm not going to show it, but let's go to the website and see how it works. Okay, so here is the website. The website is by Matt Bognar from the Department of Statistics and Actuarial Science of University of Iowa, and it has this nice applet that you can play around with the parameters alpha and beta of the beta distribution. Let's say, and you're going to see that the shape sometimes is symmetrical, like the normal distribution, but it's not always the case. So let's try with parameters 0.5 for alpha and 0.5 for beta. So here we have the alpha 0.5, beta 0.5, and we've got this distribution that is the likelihood of values very close to 0 is very large, and the values close to 1 are very large, and the ones in the middle is much lower. Now, so here it gives us a probability mass, and here is a value. So basically, if we use 0.5, then the value is here, and what it tells us is what's the probability that of obtaining a value between 0.5 or and lower, so values lower than 0.5. Well, the probability is 0.5 because it's symmetric. It's symmetric because we have the same values here. It wouldn't be symmetric if the values are not symmetric. Now, if we go to 0.4, then sorry, I have to put here 0.4 is the value I'm interested in, and it gives us what's the probability that the values are lower, so the interval between 0 and 0.4. Well, that probability is 0.43. What about if we go 0.3? Then that probability should be lower. Okay, values between 0 and 0.3 is 36.9%, and so on and so forth. This axis gives us the density. So you can see that lower values have higher densities. Now, and this curve will go when the values are very close to 0. It goes towards infinity. So actually the probability density for 0 is infinity, same as for 1. And values very close to 0, they have a huge density. Okay, so but see what happens when I change. Now when I change the value of 1 and they are not symmetric, they're not the same value, then the distribution loses its symmetry. Now if I put 1 and 1, it's going to be like a continuous distribution, a continuous uniform distribution. It gives a density of 1 to all the values. So that's a density that is very common in Bayesian statistics when we want a uniform distribution. Now if we add a 0 here, now we've got this. If we do the other way around, we get the opposite. We got values close to 0 are more likely. Now 10 and 10, we've got a if we put the value 0.5, what's the probability of values lower than 0.5. To obtain values between 0 and 0.5 is 0.5 because it's symmetric. So when these two values are the same, the distribution is symmetric around 0.5. And as you can see, the density for these values is much higher than 1. So basically, this is the beta distribution. The shape varies. It could be symmetric if the two parameters are the same, and it's not symmetric if these values are not the same. Let's change this one. So you can see it's not around 0.5, not symmetric at all. And the main property is that we can assign probability densities to values between 0 and 1.